Following is my conversation with Dr. Jennifer Prendki. Jennifer is a physicist by training, experimental physicist. As you will see in the conversation, she's so excited about physics, and so am I. And then she turned into a data scientist, machine learning engineer, and applying a lot of concepts of how to handle with messy data to the field of machine learning and data science. Jennifer has a very unique take on how to improve the methods of deep supervised learning. Today, there is a naive version of deep supervised learning where we create big training data sets, we throw a lot of compute at it to train, and just big everything. And that is not very sustainable for many reasons that Jennifer and we get into the practicality of the topic. Jennifer has perspectives, and she is doing active applied research, and she's applying those ideas in the industry as to how less is more, how we can work with data sets, training data sets that are not that big, and how to make that work. So there is some engineering and some science that comes together. It certainly is an active area of research. So more questions than answers yet, but definitely a very promising line of research direction to kind of bring sustainability to deep supervised learning. I had a lot of fun in having this conversation with Jennifer. Such fresh, original views, and she's so passionate about it. And I am just sort of, fascinated with how her background in experimental physics and data from that perspective is helping with her work on machine learning and data science. And it speaks to the power of interdisciplinary approach and people and colleagues and team members who bring interdisciplinary perspective, how they can be a lot more successful at accomplishing these goals, these objectives that require creative thinking and thinking differently and all that good stuff. All right, and now here is my conversation with none other than Dr. Jennifer Prendki. Okay, we are on. Jennifer, how are you?
I'm good. Thank you for inviting me to your podcast. This is super exciting.
Very, very likewise. And I was, as we were just talking off mic a few minutes ago, as I was looking at your background, I noticed that you have a lot of physics background, and maybe that is a good place to start, Jennifer, about physics and how your journey brought you into different facets of AI. I think it'd be good for our audience to hear about your very impressive journey.
Yeah, no, absolutely. I'd love to talk about that. So yeah, so as you stated, so I'm actually a particle physicist by training, and so people are often a little bit like surprised, like how did you make the jump into machine learning? Now, the truth is it's actually not as uncommon as you might imagine nowadays, because obviously these days you have lots of very strong machine learning programs in universities, but back to the days when I entered in the workforce, machine learning or data science degrees were far and apart, right? So it was fairly common for people with my profile to eventually make the jump. So my personal story was basically I jumped into the industry because I entered the workforce basically at the beginning of the recession, and so unfortunately all my dreams of doing fundamental research were a little bit crushed because specifically for particle particle physicist, you do rely on expensive hardware and particle accelerators to get your data in shape, right? And yeah, I mean, unfortunately, like my specific area of research was like severely affected by the lack of funding back in the days. Now it's actually very interesting because like even when I look at the market today, right? I mean, so people with like machine learning degrees and so forth and so on obviously are very heavily trained on how to build the perfect machine learning model, understand different architectures and so forth and so on. But one thing that I think even today like sets a lot of, you know, like particle physicists and even like applied scientists apart is that there was actually a heavy focus on how do you get your data, right? I mean, so I think like this is something that differentiated me from the beginning, that collecting the data was a very like intrinsic part of the job, when in machine learning, traditionally, like people expect the data set to be already ready and available for them to work with, and that wasn't the case in physics.
That is such a true statement. Did you, Jennifer, get to go to places like CERN or other particle accelerators as part of your
yeah, absolutely.
Your physics journey?
Absolutely, that was a complete part of the job. So basically, like, so actually the story was so I started my PhD basically at the same time when you know, like the new CERN accelerator LHC was basically like starting, like just a couple of months before it was getting launched, right? And so I was one of the few lucky people to see the LHC essentially like completed and could still visit the, you know, like basically the place before you know, like basically radiation would make that impossible, etc. So I mean, and eventually I did my PhD on an experiment that was based in, at SLAC in Stanford, because I actually wanted to work on an experiment that already had collected data in order to avoid working solely on like simulations at the beginning, because that's something that particle physicists do a lot of, like work with Monte Carlo simulation and sort of thing. So I wanted to work with the real thing. And so, yes, during my PhD, I had like multiple responsibilities to work with the engineers on the data collection process itself. I work on shifts to get the data in shape. I was actually responsible for data quality management for the experiment I was in charge of. And so, yeah, obviously, like that gave me a lot of opportunity to work with messy data.
Look, I think, you know, as you mentioned, that all that experience of working with messy data and with a lot of data, that how relevant that is to Jennifer, all the AI journey, which we'll talk about here in a minute. As I was, Jennifer, preparing for our conversation today, I always reach out to colleagues in industry and see, hey, if they have got questions and all that good stuff. It was interesting that when I shared with few colleagues your background in physics, I got questions like that, hey, Jennifer, what's your take on the standard model? And it looks like there is a lot of structure there, meaning there are three sets of particles. You know, there is a, you know, electron, and there is a muon, and so on and so forth. And then there are these corresponding neutrinos. So do you find, it looks like there's a lot of elegance in it and a lot of sort of, you know, different versions of the same particle and whatnot. It looks like somebody's, for a lack of better description, somebody's software code or program. So the question is, what do you think about?
So I will give you like a very like data scientist kind of answer to this. Is basically like all models are wrong, some are useful, right? I mean, so I believe exactly the same thing of particle physics, generally speaking. So is the standard model wrong? Absolutely, right? Because we'll never be done actually like understanding like the complete universe. We're building models just the same way like a particle physicist's job is to try to reproduce a model that can, you know, like explain like how the universe functions, how the different interactions between like matter and antimatter, etc. Functions as closely to reality as possible. but you're never done modeling. You can always get a better model. And, so yeah, I mean, absolutely, like there's constantly changes, and lots of changes have happened since I jumped into the industry. I keep following them, but so it's like absolutely not surprising to me. It's just like how closely can you get to the real thing? A model will never be 100% of
I
the
think you
reality.
said it so well that all models are wrong. Some models are useful, and eventually models keep getting replaced with better models. So in your opinion, Jennifer, has standard model lived its useful life? And is it now waiting for to be replaced with, you think, something better? Also, from the future, this is now a question from the audience, from the future of physics perspective, when you hear a lot of people talk, even who are experimental physicists at CERN, they say things like, my job is a lot about data processing. My job is a lot about statistics and machine learning. So at some level, you hear this thing, we have this world's biggest machine, the biggest collector of data. So it collects a lot of data, a very high fidelity, high granularity, all that good stuff. But then once it's collected, then all the analysis of that data and model making and whatnot before somebody could do cool theoretical physics and mathematical physics with that. Experimental physicists are looking for statistical correlations and 5 sigma or whatever that is, and it looks like that there is in experimental physics and machine learning, there are a lot of nice overlaps, a lot of data, messy data, need to do the data analysis before somebody comes with the next string theory and say, oh, all the data and experiments that you guys have been conducting, I now have a very elegant mathematical theory for it. It looks like that, that comes at its own time and pace. And but meanwhile, experimental physicists, they are using a lot of data analysis, data management, and machine learning type tools to do their job, which also makes them then excellent candidates to do machine learning in all other fields of interest.
Yeah. It's interesting you would say that, because I was actually like back in the days when I was doing my PhD, I actually worked on like you couldn't call that deep learning. That was like a neural net with 6-7 layers, but we're actually implementing neural nets to separate the signal from the noise. So absolutely even 10-15 years ago, people like me were basically using machine learning tools for data analysis in particle physics, right? I mean, which made us obviously a good candidates, etc. Right? And I'm sure this has evolved tremendously nowadays, right? But to go back to your question on basically do I feel the standard model is still useful? Yes, absolutely, right? I mean, so basically it's always the similar question also related to physics is basically, can you explain the fall of an object using Newton theory instead of using Einstein's gravitational theory, right? And so yes, you can. And so when is Einstein theory necessary, where basically Newton theory doesn't work anymore? Is going to be very large objects or very small objects where you need to apply quantum field theory instead of using a regular gravitational calculation and so forth and so on, right? I mean, so it's always about the outliers. The same thing happens in machine learning as well, that basically when you make a better model, usually that model is going to be better because it addresses the corner cases and the outliers a little bit better, right? And usually the typical middle ground kind of normal data that falls into distribution, you can explain with fairly simplistic models, right? And so basically I mean, I see a lot of similarity when you see nowadays some machine learning researchers who are attracted to building very sophisticated models with very complicated like sets of parameters. Like just take the example of like those crazy large NLP models, right? I mean, GPT, etc. Yeah, I mean, do you really need this for your application? You might not need this for, you know, like an everyday like chatbot application, right? I mean, so I see the exact same, like, you know, like maybe like a difference in the level of pragmatism between like an experimental particle physicist and a theoretical particle physicist, and like, you know, like different degrees of machine learning researchers, right? And maybe the people who work for, you know, like a startup, a large company that are trying to like build like you know, like recommendation systems, search relevance, etc., are going to be more pragmatic and often like opt for a more simple model as opposed to like going for the crazy large yet very accurate and very data greedy kind of options as well. The same applies to physics as well.
Very well said. Do you think, Jennifer, just lingering on a little bit with physics for a few more minutes, where do you think the next breakthrough in physics will come from? It looks like, and again, I'm talking from a layman's perspective, it looks like that string theory is losing its popularity. Quantum field theory has kind of become the de facto standard and has now morphed into quantum information science and quantum computing, where, you know, everything looks like is a quantum computer. Everything is a qubit. You know, universe is like a big quantum computer. You know, and then there is still general relativity out there, still a very sort of, you know, successful classical theory of general relativity and attempts to bridge between general relativity and quantum field theory have not been very successful. So where do you see, it looks like physics is at some kind of crossroads. Where do you see, Jennifer, with all your wonderful knowledge of physics, over the next 10, 20, 30 years, what should we expect from physics, or where will you think the new physics come from?
Yeah, no, so you kind of like already gave like part of the answer in your question, right? Because like you're right that, you know, like quantum field theory becomes like the de facto like theory nowadays, but actually, so it's really nothing new, right? I mean, what quantum field theory is really about is like, as you said, bridging you know, like general relativity and quantum physics, basically, right? And so basically, like you're kind of bridging like the infinitely large and the infinitely small into one theory that explains everything, right? I mean, so going in that direction with, yes, I think like eventually like we're on a path to unification. That's what physicists want to do, right? I mean, create like the theory of everything that's like a set of equations that doesn't just explain like the infinitely small, the particles, the neutrinos, and so forth and so on, but also explains like you know, like the way like galaxies interact, dark matter, and everything else, right? I mean, so there were always like basically like, you know, like even nowadays, like we still don't know for sure, or we still have like lots of questions about like what is dark matter, what is dark energy, etc., etc. And so in fact, when I did my my master's, like basically I actually had I was part of you know, like a program where people studying were like a mix of like astrophysicists, cosmologists, particle physicists, nuclear physicists, and so forth and so on. And so we were encouraged to look at things from a multi-directional standpoint, as opposed to just like, so basically it wasn't a master's of like particle physics, right? It was a master's of like actually the program was really about like bridging, unifying. So obviously it's going in this direction, right? And so to some extent, it's like basically like, is this the same direction we're going towards when you look at machine learning, where you want like, I mean, this is basically what AGI is going to be, right? I mean, if we get there, where you have one single, like basically like unit system model that can explain and like provide intelligence, generally speaking, and not just like a translation model, an autonomous driving model, a lane detection model, a facial recognition model.
Yeah, no, very well said. In fact, one person, Jennifer, did ask a question regarding dark matter and dark energy, and also about black holes. And the question is, since we keep hearing that, and I'm certainly making things very simplistic here for our conversation, that most matter and energy in the universe is dark matter and dark energy. And the word dark comes from that, hey, we can feel the gravitational effect of all that mass and energy. Without that mass and energy, we cannot explain the speed of inflation and many other things. And it's everywhere. So the room where you are, where I am sitting right now, dark matter and dark energy is present here. It's not that there are some special parts of the universe and only there is dark matter and energy. It is everywhere. It is in us. Then the question then is, since it's not, interacting with electromagnetic sort of force or other forces of nature for that matter, is it possible, this person asked this question, that there are creatures living amongst us? It's a silly question a little bit, made up of dark matter and energy, and they are here living in their dark matter universe, and we can't even notice them because somehow they are in their own space and we are in our own space. And I promise that I'll ask, as silly as the question might seem, I will ask you that. So maybe if you want to comment, Jennifer, upon that, is it possible that there are aliens living amongst us, made up of dark matter and energy?
There might be a double of you in dark matter, like absolutely right. I mean, so one thing I notice is like people usually like don't quite understand the difference between like antimatter and dark matter, right? I mean, so
can you please explain? That is very true. That what?
No, of course. So antimatter is basically like the way that it goes back to like the way the universe was created, right? I mean, so when you had the Big Bang, there was no matter, there was only energy, right? And so basically from energy you can create matter, but for the sake of conservation of like all the laws of nature, etc., every time you generate a particle of matter, you need to have a particle of antimatter that's generated at the same time, right? I mean, so basically if energy gives birth to an electron, it needs to give birth at the same time to an anti-electron, right? I mean, so which is called a positron, right? The same is true of any particle, right? And so actually that was like one of my specialty, like my focus for my thesis was like basically like technically, if just the same way that these two appear together, they annihilate each other if they meet each other, right? I mean, so basically, like if an electron meets a positron, basically, like both disappear, and you're just left with energy, right? And so basically,
Jennifer, I have to ask you a quick silly question, Jennifer, if I may.
Yeah.
It looks like, Jennifer, on Earth, or maybe this part of the universe we are in, and maybe that is true for observable universe, period. It seems to me that we see a lot of electrons. Where are all the positrons?
No, that's exactly. Let me explain. So this is my my area of research. So basically, exactly what as you said, right? I mean, so it's like if for every electron there is a positron, if they annihilate each other, eventually we should have disappeared, like even us as people, because we are made of matter, not antimatter, right? So the reason why this happens is basically like there is an asymmetry in the behavior of like matter and antimatter called CP violation. And so CP violation basically states that matter decays slightly slower than antimatter, right? And so this causes an asymmetry. So basically, we are the result of what remains as a cause of this asymmetry. And so what's interesting is like basically this asymmetry is very small. It's like something of the order of like a 10 to the -3 to 10 to the -5, right? Depending on the type of particle, right? And so typically you have a lot of PhD students making like centering their PhDs on like measuring exactly what the asymmetry looks like by generating particles with the particle accelerator and measuring like basically like the remnants afterwards, right? And so based on this, like the visible universe is just basically like the overflow, right? I mean, basically what survived because of this asymmetry, essentially, right? I mean, so this is well understood. This is tangible. Like we can actually measure, we can see those antiparticles. Just basically like when you measure them, if they come interacting with matter, they're going to disappear, right? And then dark matter is something, yeah.
Before we go to dark matter, Jennifer, just a quick question here. You really got me so intrigued. So if I heard you correctly, if we generate or when we generate, and you said it's a very well understood phenomenon now in the lab, an electron-positron pair, that positron is the antiparticle for electron, and I assume that it probably has the same mass, but it has a opposite charge and maybe some other opposite properties. And if it comes into an interaction with the electron, they both will annihilate and give back energy or some other particles or what have you. But if I also heard you correctly, you said that, hey, electrons sort of, decay curve is different from positron, or meaning electron has much longer life than positron. And we can see that even when in the lab, if we create an electron and positron, we can see that positron decays quickly back into energy, but electron stays. Did I hear you, Jennifer, on that one correctly? That is what happens?
The little caveat I would add is like, it's more true for other more unstable particles, right? Because electrons are extremely stable, so it's gonna be hard to like measure decays, but like that's true of like neutrons, right? I mean, a neutron's like a lifetime is like 21 minutes, and basically like the anti-particle that matches that, like an anti-neutron might be like just a tiny bit shorter than this, right? And so when it will decay,
so the anti-neutron, would decay quicker than a neutron.
A tiny bit, right? I mean, so basically like by a few, like it depends on the particle, like a few, like a 0.1% or something of that order, right? And so basically and then it decays on like its own set of anti-particles, right? And then like a mix and so forth and so on. And then basically, because it's another particle, that other anti-particle is not gonna decay directly or like interact directly with the original one, because you need the anti-particle to annihilate with the original one, right? I mean, so this is basically how you eventually end up with a situation where there are lots of remaining, like existing, like sustaining real particles of real matter.
Do you think, Jennifer, for quite some time to come, we will continue to discover new elementary particles? Like, today it looks like neutrinos and quarks and electrons, they are organized, in that standard model.
Yeah, I mean, so basically that's exactly what going beyond the standard model is, right? Because the standard model is basically based on like 6 quarks, so quarks being like the sub particle that big like neutrons, like all of these things and so forth and so on, plus like like the other types of particle like electrons, etc. And then like basically like when people discovered the Higgs boson, that was already beyond the so I mean there was like in theory there was a Higgs boson in the standard model, but then there is a range of like other particles or like types of bosons that don't really fit into this. So basically like as long as we will keep finding new particles, it might or might not fit in the original framework, right? I mean, so basically what experimental physicists spend a lot of time doing is basically like look for the missing particles that theory says should exist in the context of the standard model, but haven't been observed yet. So basically the Higgs boson was an example of that, right? But then every now and then you're gonna find something like, wait a second, this particle doesn't match any known mass, any known behavior, right? And basically it's just like, where does it fit in our model? It doesn't, and then this is where you need to go beyond the original model you had in place, right? So,
Fascinating. Very last physics question. Is space-time made up of or a result of quantum entanglement and that sort of a thing? Or what is the relationship between quantum nature of things and space-time? It looks like in some of the modern literature of physics, it kind of space-time seems like an emergent property of quantum systems and quantum behavior. What's sort of your take on that, or anything that you would like to share?
I don't think it's so well, like it's, yeah, like it's almost like a metaphysical question at this point,
Yeah.
right? I mean, so basically, but like, I mean, so yeah, in the context of like relativistic theories, basically, like, you know, that time is considered as being an additional dimension, right? I mean, so technically, we perceive it as being a different type of dimension than basically like you know, like a actual position in space, etc., etc. But that's because us. So in this case, you could say like this is a perception in the human brain of basically what time is supposed to be, right? I mean, and so, but I mean, that's exactly the sort of questions you're trying to answer by like unifying everything together, right? I mean, it's basically like you know, like in the context of quantum field theory, basically, like you can consider just the same way that you consider like a particle as being or a particle as being either a piece of matter or, you know, like a wave, right? I mean, so basically the same goes for like lots of concepts in particle physics, right? I mean, so what's interesting, like from a modeling standpoint, because again, we're talking about modeling here, right? I mean, so it's like time can be at the same time a dimension, but also something else in the context of another theory, right? I mean, so it's all about like finding the right like mathematical framework to make all of this fit together so that it like it suits well together and you don't have to be in a either or kind of situation.
So true. Which now brings us into our topic of artificial intelligence and machine learning. I just was absolutely fascinated by your very differentiated take on how it should be done compared to how it is being done today. But before we, Jennifer, get into it, just to kind of set the stage, what is intelligence, and then what is artificial intelligence, and then as a sub branch of that, uh, what is machine learning? So if we start with maybe intelligence, and then all these other questions that stem from it.
Yeah. No, so first and foremost, right? I mean, so we can talk about machine learning, we can talk about artificial intelligence, and we can talk about machine teaching, right? I mean, so basically, like one of the things I will say first is like, so the most common type of machine learning, when somebody says, I'm studying machine learning, I'm doing machine learning, usually they will talk about supervised learning, right? I mean, so supervised learning is the case where you need to learn from past examples, like what's going to happen in the future, right? I mean, so basically, like it's like by looking at lots of images of cars and pedestrians, you can basically learn to predict cars and pedestrians from new pictures that your model hasn't seen yet in order to build autonomous driving software, right? And so what everybody does in this space is like, and everybody knows it's a huge issue, is like you typically need a lot of examples before you reach a certain amount of accuracy, right? I mean, so this is the perception that we all have, right?
Yeah.
When you think about what it takes for a baby to learn what a cat looks like, it does not take hundreds of thousands of pictures, right? I mean, in fact, in many circumstances, like you see one cat, two cats, maybe if like you see a new cat that's like a little bit different because it has a shorter tail or like a different, like color and so forth and so on. You might need one more example, but we're talking units. We're not talking hundreds of thousands of examples, right? And so in other terms, like basically what I'm trying to say is like basically supervised machine learning, which is the vanilla, like kind of like state of the art, like for most use cases today, is not intelligence, it's just repetition, right? I mean, so it's like a generalization of a use case. And
question, Jennifer, on that one, on supervised learning, as you said, that it is today the prevalent sort of, most of machine learning today is supervised learning, and you rightfully mentioned the need for all this training data, well-labeled training data. And then you so eloquently gave this example that we as people can learn with few examples, even when we as babies. So any intuition, Jennifer, our audience kind of has an idea of how the machine learning model works. So they know there is an input space, which is the data. Somebody have labeled it, that is the output. And at a very simple level, the machine learning is y equals f of x. It is trying to learn a function from that data, and there are ways to do that. But in fact, this is a question from the audience as well. Do you have any intuition as to why we as people
Yeah.
are able to do much better and learn with fewer examples.
Yeah.
Are we using, are we just better, our neurons better modelers? Are they wired in some smart way? Are they using some special algorithm? What is it? What is the difference? What is your intuition, Jennifer, on that?
It's in my opinion a combination of many different things and many different facts at the same time, right? I mean, so one example, so first and foremost, right? I mean, so when you use supervised learning in robotics, in machine learning, you actually start completely from scratch every single time, right? I mean, so basically what I'm like, what you have to consider here is like, you start with a model that knows nothing about nothing, right? And so if you have to like help this model differentiate between cats and dogs, you're gonna have to show examples, right? We as people or animals or like many other circumstances, like you can use like the equivalent of transfer learning, right? I mean, so for example, it might be easier for a baby to learn what a cat looks like because they already understand the concept of a pet, right? Or they understand the concept of an animal, right? I mean, so they will already expect that there is some fur on it, right? I mean, they will already expect to see a tail, right? And basically because you're not starting from scratch, just the same way that transfer learning, which is the case where you take a partially trained model and you just basically like make this fine tuning in the end where like I already know what a dog is, now I just need to like learn how to differentiate a dog from a cat by knowing like a cat has pointy ears, has a longer tail, has a slimmer body, and so forth and so on, right? It basically helps you get there a lot faster, right? I mean, so we don't segregate that information, right? When we learn, we already have information we have acquired before, right? I mean, and so we also don't know, like basically that's a question about, like medicine, genetics, and so forth and so on, but like some of the knowledge might be inherited from, like your brain at birth might already be pre-trained in some way, right? I mean, so basically like, and then, like these are questions for neurosurgeons to discover and then so forth and so on, right? But like, so I think a lot of like, the inefficiencies that you still see today is basically like you don't have this dimension, right? Another aspect to me would be like the concept of learning to learn, which is sort of associated to that, right? I mean, so basically every time you learn a new concept, you learn tricks that work for you, unlike how you learn, right? I mean, so in your case, maybe you learn a new language and you realize like, you know what, this specific book was super, or this brand of like, books was super helpful for me, or like I learned more easily by listening to radio in a foreign language in the car when I drive, right? And so basically like understanding how you learn is basically making you more efficient at doing this, right? I mean, so basically like there is an aspect where building the model itself, like basically you need a meta kind of layer on top of this, right? I mean, so basically when you build the model doesn't have like feedback loop on itself, right? I mean, what's working for me and so forth and so on, right? And so this goes into machine teaching, right? I mean, so basically like we can talk about this for a long time, but basically like the next generation compared to machine learning, which is the case where you overfeed your model with a ton of data until you hope eventually the model understands the difference to the level of accuracy you wanted, right? You can be more strategic and try to like actively kind of like decide, select, focus on like areas of weakness in particular, just the same way that if you were to teach a child, the child already knows how to do like addition and subtractions, and basically you're like okay, now I know I need to focus on multiplications in particular. You're not gonna waste your time again on what the child already knows, right? And so the learning to learn aspect is like having your own brain providing its own feedback loop over itself, right? I mean, so basically, and so I think that might come from consciousness, right? I mean, essentially, right? I mean, and so, so machine learning teaching is like kind of like this state in between where you have this intelligence, like making it like more, targeted what you're gonna learn from. It might be something that comes from the outside, so it's still not as evolved that basically our brains, right? But like it's halfway there, right?
So then, Jennifer, the natural question that emerges from that is, what is your suggestion for all the communities out there that are working with supervised learning in many different domains. And what are your suggestions for them from an architecture perspective or transfer learning perspective? How do we get better at the craft of supervised machine learning? Because supervised machine learning is here to stay. It has a lot of momentum right now. A lot of people are working on, so which tells us that it will stay probably for some time before it evolves into something else. But while we are doing it, how do we do it better?
No, and it's like, it's here to stay because it's the basics, right? I mean, you still need this in the first place. Like the paradigm of transfer learning, like technically, like you don't start from zero, but like the training process remains the same, right? I mean, so basically, like I don't think anybody who's like investing time in learning, like supervised learning, or like universities focusing on a curriculum around this have it wrong, right? I mean, you need to know how it works because like you have to start somewhere, and it's a fundamental piece to the greater puzzle, right? What worries me as a professional in data science, and actually like one of the reasons why I became like an advocate for like less data is more, and basically like starting the sort of initiatives and the company I'm running today, right? I mean, so it's basically like we got like almost like complacent in making it all about the hardware, right? I mean, so historically, when you look at how people get to where they are right now, first and foremost, like a lot of people do not realize this, but like even deep learning, neural nets, like back propagation, which is the center of like the learning process of a neural net, right? All these things have been around since like the 40s, 50s, 60s, and so forth and so on. Nothing is new. But the reason why we saw this boom in like new like computer vision applications until recently was essentially we did not have the hardware to, number one, collect the data, right? I mean, so we did not have the data at the same time, right? And we didn't have the compute to process it, right? I mean, so basically, like this is why we landed in this succession of AI winters where researchers were making amazing progress, and then when you wanted to put this into application, even the army didn't have the means to basically like test it in real life, right? And so we got used to basically like the moment where now we have like hardware that's super fast, we have like GPU machines, we have cloud compute and so forth and so on. Like it enabled basically like to test all of these things, right? But eventually it's like because like we got spoiled suddenly with better hardware, people didn't challenge themselves in finding other ways, right? I mean, so instead of basically like it's like it was so easy to acquire like specifically with cloud compute, right? I mean, you just sign up to like a GCP, AWS, and you can basically be up and running in computers that you don't even have to buy, right? I mean, to basically train your models. People are just like basically, why would I even bother? Like this is working for me. Why would I bother being smarter about my data, right? And this is becoming a problem because this has landed us in a situation where now we live in the age of what I call the big data lobby, right? I mean, so there's like we have like organizations that make money fundamentally from the amount of data that we use, right? And so you can guess who out there, right? I mean, obviously has a huge incentive in believing that you need to use more data no matter what, right? And so at the same time, this is not wrong, right? Because if you have a lot of data, you can obviously like your model is going to get better. The question is why? The question, like I can answer that question. Basically, it's because when you have a high volume, you have a higher likelihood to find something relevant, interesting, and meaningful, right? It's just like the same way that if you go in a large library, you're more likely to find books you're going to enjoy reading, right? I mean, as opposed to going to a smaller one, right? It doesn't mean you're going to like everything. It's not going to mean, and in fact, you might find more garbage in a large library, right? I mean, and so what people kind of miss, like, is essentially that we don't need volume, we need variance. We need diversity. We need the right examples, right? And so we need to put more work into understanding how do we create high value, high variance data sets instead of like throwing the kitchen sink at the problem, right? And so this is incredibly important for people in business, because when you observe the news nowadays, like in machine learning, you have so many amazing initiatives, you have so much research, like really meaningful things, like we're able to like make pictures talk, right? I mean, we can basically pretend to be other people and so forth and so on, right? All of these things that we can do, but at the end of the day, most organizations complain that they're not getting a return on investment on their initiatives, right?
Yeah.
And this is because if it costs you $2 million to build this model because of compute resources, because of, you know, like the training time it's going to take, because of data annotation and so forth and so on, right? If you don't sell your product for more than this and substantially more than this, you're going to be underwater anyways, right? I mean, so we live in this age where a lot of our models are very like worthy from a technical standpoint, but they are not worthy from a business or a monetary standpoint. And so really look like it's all about like you know, like for companies, like usually it's about like making money anyways, right? I mean, so if they don't see a return on investment, eventually they're gonna drop these initiatives and we're gonna fall into the next AI winter, right? I mean, so for me, like we live on great danger of basically having more and more organizations essentially complain that, you know, like I love what you're doing, this is an amazing app, I you know, like I can see like how this is helping me on a day-to-day basis, but at the end of the day it's not helping me make more money, so I'm stopping this, right? And unfortunately, like a lot of like machine learning scientists, specifically people who graduate from universities and are trained to think as scientists as opposed as business people, basically don't realize that this is a grave danger that basically we are under, like as a community.
So true. Jennifer, on that note, if you were to take a further deeper dive into it, on this topic of less is more, which by the way, I totally agree with, how do we go about in a given domain building this high value, high variance, diverse data where a relatively small sample set can serve the needs for training? So are there methods, practices, research around it that you please share that is going on or should be going on that can educate us as practitioners? I'm a software engineer myself. That how do we do this compared to this notion today that let's collect a lot of data and let's do some kind of semi-automated labeling. So today's practice is, okay, let's have a lot of data. Let's first humans do some labeling, then let's have machines do some labeling, then humans can do the QA on that and correct, and then machines can label it again. And those are the type of methods today that are used to create large training labeled data sets. So how do we construct high value, high variance, diverse data sets where less is more? Give us some recipes and some practical ways to think about it.
Yeah. No, so what you mentioned here, right? I mean, so basically using machines models to like annotate the data for me is like, there is value in the idea, but this is the wrong way to go for multiple reasons, right? I mean, so first and foremost, like simply put, essentially, like you're solving data annotation, like the challenges associated to data annotation, you're not solving anything else. You're not solving the performance of your model. You're not solving the compute problem. You're not solving the storage problem, and you're not solving the data collection problem, right? I mean, so if you look at an autonomous driving company out there, look at Cruise, look at Waymo, like you can see their vehicles like driving around like needlessly for hours, like in the center of San Francisco. And I don't think anybody really knows like what they're collecting for, right? I mean, so it's just like eventually something interesting is gonna happen. Hopefully this is gonna help boost my model, right? This is absolutely the most wasteful thing that you can do. Unfortunately, a lot of people don't do and don't know any better, right? I mean, so what I think like it all starts with like making a conscious effort in understanding how our machine learning models learn and understanding which data helps, right? I mean, so you can go into like the conversation around explainability. When we think about explainability today, usually you think about like my model made a specific prediction, why or what factors impacted the decision, right? that is not like, and a lot of people in fact will be like eventually get comfortable with the idea of using a black box, because that insight alone is not actionable, right? I mean, knowing that somebody's loan got denied because they are from a minority, because they're too young, because they're not making enough money, like might be enough from a compliance standpoint, but it's not going to help you as a machine learning scientist say like, what do I do to have a fairer model, right? So what I think in terms of explainability is like what I would call an understandability, is like, why did your model learn this in the first place? And so basically like understanding which part of the data caused that belief in the first place is key to a lot of the problems we have in machine learning nowadays, right? So the approach that we use at Algo, right? I mean, so basically it's like fundamentally is like basically like I felt like, you know, like I have run teams. I've been a practitioner myself. Every single time it's like I never got the resources I really needed to like prepare my data sets and basically train my models from an annotation standpoint, but from everything else as well, right? I mean, basically like didn't have enough AWS credits. I didn't have powerful enough computers, etc., right? Or like my models would take very long to train, right? So I felt like there was a need for a tool that would basically like try to like understand what's going on. So basically like what you can do, like we started, and so this is something everybody can try. It's actually fairly simple, right? It's basically like there is a training paradigm called active learning. So active learning is not something we invented, right? I mean, it's basically like it's essentially like a step-by-step training process. It's an incremental learning process where you have a very large data set. Instead of preparing this entire data set and using this as your training data set, training your model with it, you take a tiny bit of data, right? So then obviously there are questions about like how much is enough and so forth and so on. Obviously that's a more deeply technical, complicated question to answer, but assume you know how much you want to start with, right? So you start with a little bit of data, you get that data annotated, which might be 10% of the data, 5% of the data, 1% of the data, it doesn't matter, right? You train your model with it, and then you end up with like version 1 of your model, right? I mean, and so at this point, because it was trained on a subset of your data, you shouldn't have your hopes up that this model is going to be anywhere close to what you need it to be, but you have a starting point, right? And so you use the starting point to essentially run predictions and inferences on the rest of the data set, which you haven't used for training just yet, right? I mean, so if you selected 1%, at this point, you have 99% of the data set, which you can almost use for validation. However, you can't call that validation, because validation would be to say, like, look, this was predicted as a dog, but it was a cat. At this point, because it's not prepared and it's not annotated yet, you cannot draw that conclusion, right? So what people normally do is like the most like straightforward thing you can do is like say, I'm going to check with what level of confidence that prediction was made, right? And so the most like vanilla standard way of doing like active learning in this case is to say like whichever record was predicted, or like the 500 records, or like the 5% of records that were predicted with the least confidence are basically the ones I should pick, because confidence is a proxy for the model has been struggling with these things, right? I mean, and so basically it's almost like low confidence is a proxy for usefulness. So that's a very good starting point. Now, the reason why usually it doesn't cut the mustard is basically like, imagine you're working with corrupted data. Imagine you're working with, you know, like an example I always like to use is like you're building a sentiment analysis model that's meant to work on English tweets, right? And then unfortunately for you, some fraction of your data has, you know, like German in it, right? I mean, or a foreign language or something that doesn't really like isn't understood by your system. If you run this process of inference, you're bound to have a low confidence level, right? Because the model is not going to understand this data, right? So using that proxy and saying like low confidence means I used to use this, guess what's going to happen? You're going to enrich your data set with more of the data that you don't want, right? I mean, so this is why a lot of people who would give it a shot to active learning in real life and in the industry usually say like, it's not working, I'm gonna give up, right? Now, where I see things going and where we're doing a lot of research, right, is basically like, how do you take it to the next level? How do you truly understand where the model is struggling? That's the question, right? Can you build like a process or a model that can basically like accurately predict which records the model is truly failing with, right? Or correct, like basically like struggling with, and so forth and so on, right? Just the same way that, like you have like you ask it, you teach something to a child, the child like basically like answers the question with scratching their heads. You can say like, he gave me the right answer, but like I know from like analyzing this behavior that scratching heads is basically like usually a sign that they're not sure, right? I mean, so this sort of things, right? So, and this is where the understandability part actually comes here, right? I mean, so, and this is where the machine teaching part comes in, where you can build this external process that essentially like analyzes, monitors, and supports the training process from afar, right? And so active learning is like the ancestor of what we need to build, right? I mean, it's like basically like the first version, which is like very barbaric to some extent because it's so simplified, right? But it's a good idea, right? Just the same way that you have a concept of active learning in psychology for children, where the teacher tries to adapt like basically their the way that they teach for specific children in particular. You can do the same thing for a machine learning model, right? And this is something that unfortunately is like either not completely like popular in the industry just yet, or the people who attended it are basically realizing this isn't working for them and they just give up, right? Just the same way that the best analogy I have is like 10 years ago when deep learning was starting to get popular, many people would give it a try, but then essentially they would give up because they realized that, this isn't working for me. And the reason it wasn't working is that the hyperparameter tuning piece wasn't done properly because people didn't know how to, right? And so we're exactly at the same phase where, people are sometimes dabbling a little bit with it, but not really understanding why they're doing things wrong, why it's more complicated than it sounds, right? I mean, why the, a basic, rules-based active learning is not really a good idea, right? That's all. So I'm a very strong promoter of luckily, there is a lot of research in academia on those topics nowadays, but like this needs to arrive in the industry as well.
Anything that comes to the top of your mind as to what should people study to familiarize themselves with how to do this kind of less is more active learning? And I'm talking about practitioners, meaning software engineers, ML engineers, data engineers who are not scientists. They are practitioners. They are trying to solve an engineering problem with whatever the tools are that are available to them. That what is your suggestion for all these engineering teams out there who are working on these types of problems?
Yeah. No, look, it's a very nascent space, right? I mean, so luckily, like there are like, I mean, you can obviously like there are a couple of like state-of-the-art papers which actually might not be so up to date anymore, right? I mean, so basically, like I can absolutely share that like offline afterwards. I mean, there are open source libraries that are like sort of like providing the framework. Something that's important to understand is like, so I mean, obviously, like when you think about active learning, it's really like an iterative process of like selecting some data, preparing or labeling this data, training with that model, inferring on the rest of the data, and using that piece, the inference data, to basically inform the selection of the next loop, right? And just the way I said it, it should sound like from a machine learning ops standpoint, right? It's going to be hard, right? Because we're already struggling, like knowing how, when to retrain a machine learning model. Like basically, like at this point, you need a process, you need tools where you immediately retrain the model with like additional data. So it's like, like eventually, like when we're really mature as an industry, like this will be like a, undifferentiated from online learning. It's going to be undifferentiated from like a real-time deployments and so forth and so on, right? I mean, nowadays, if you're going to do that yourselves, like you need to be prepared, like from a machine learning engineering standpoint, to have a way to version your model, right? Because you're not dealing with one version of the model anymore. You need to have like a time-dependent models. You need to have a way to make everything reproducible, because in our framework, a lot of like, think about it that way, right? I mean, so in fact, we should probably talk about this, right? I mean, so basically like from one standpoint, you want to use active learning as a way to like prioritize the most interesting data so that your model is trained with the high impact data. And your hope is like by training on only 30% of the data, you'll already reach the accuracies you're looking for. In fact, what we're often successful in doing is like you prioritize the data so well that the learning curve drops at the end, because all is remaining, that's remaining at the end is the harmful data that actually confuses the model. Just the same way you prepare for an exam, you know everything, and then eventually you read this one more book and you're like, wait a second, now I don't remember anything about, you know, like what I thought I knew, and so forth and so on, right? I mean, so you and like the people generally speaking, like usually see active learning as a training paradigm to get to the level of accuracy that they want with the minimum amount of resources, or the minimum amount of annotations in particular, right? What people kind of like miss, which is like kind of like a shame in my opinion, is like if you can access the order in the data, right? I mean, by just like, I mean, at the end of the day, like the ordering of the data is a byproduct of this process, right? And so basically like you're gonna reach like a model which hopefully in the end is higher performance from the one you would have gotten by training on the entire data set, or at least as good as what you would have gotten on the entire data set. But something that people have never really done before we started doing this is like basically analyzing what happened. Why is this data? Because like the sooner the data is selected, the more valuable it's supposed to be, right? And so by creating a system, an engineering system where you can say like, show me like the statistical distribution of the early stages compared to the late stages. Let's say you're gonna realize, and this is a real thing, where you're gonna see like autonomous driving models prioritize data that has more cars, but then deprioritizes the car and focus on the pedestrians later, right? It's telling you something about your model. It's telling you something about which type of data is going to impact that specific model, right? I mean, and so this is something that really like you know, you were asking for like tools for how do you know which data you need to collect. You can convert this into a framework where you can collect more of the good stuff. In fact, we work with synthetic data generation companies to basically like inform them, like, you know what, like the images that contain, you know, like a winter scene or like a high density of pedestrian, high density of trucks were considered to be more useful by the model. So now you know what you need to generate more of, right? And so anyway, so basically by like what I'm saying is like by being like more, you know, like this is obviously a machine learning problem. It's a research problem, and that's something that academia has understood really well, because there are more and more problems and more like papers on the topic, but it's also really an engineering problem where you need like a ML Ops 2.0, right? I mean, where basically like you can like version the subsets of data that were used. You can analyze, you know, like what's interesting to see as well is basically like how the fluctuations in the predictions, where in the beginning an image would be understood as a cat, but later on it's understood as a dog, and then again as a cat. Why did you have this hesitation in the model, and so forth and so on? There's so many things we can do in terms of like becoming better at focusing on collecting, synthesizing the right data, understanding or identifying which data has been corrupted, which data has been mislabeled. Because if a record is mislabeled, chances are this will show in the reaction of the model, right? Just if I show you something that you were not expected to see, you will get confused. And so how do I measure confusion? Because you're gonna have, you know, like wide eyes, you're gonna have like this little bit of a facial, like you know, like a reaction, and so forth and so on. How do we measure this in the model, and how do you use that to your benefit, etc., right? And so on. This is like a completely wild area. Like I would consider this like you can consider this machine learning teaching or machine learning 2.0, right?
Yeah, no, this is fascinating. So again, just extracting the essence of what you talked about. So it looks like that annotating a small set of data could be a starting point of this journey.
Yeah.
And then using the iterative approach that you described, you find out what type of data you need more to really disproportionately impact the quality of your learning, which then can inform either you were to go to a real life organic process to say, I need more of this data, or or you go to your synthetic data factory and you say, these are the types of examples that I need more of for you to create, and that sort of a thing, and then that iteration to continue. Question for you, Jennifer, in that sense, what is your thinking on the role of synthetic data if the probability distribution is understood and correct? Assuming with that assumption, so it's certainly a big assumption, but assuming that, is it okay to then in these steps that you mentioned, that once we know what type of data will help, then for us to generate synthetic data? So just there are, it looks like several camps on the people who like synthetic data, people who don't like synthetic data. But I am just looking for sort of a scientific input on where synthetic data is helpful and where it is not.
Yeah. No, look, so we're literally doing this nowadays, like with several of our customers, right? I mean, so basically, let's talk about this because this is really important for many different reasons, right? So you correctly pointed, like I think you summarized it in a good way, that basically, like, it does make sense to have an initial data set, synthetic or real, right? That's small but like well distributed in your data space, sort of like a good representation of what your data might look like, and basically like use an active learning process or something similar to what we're doing to say, like, wait a second, the images that had a super high density in children are actually harder and more challenging for the model to learn from, or does contain more information, right? I mean, and so you basically kind of like matching like usefulness with like impactfulness on the model, right? And so we do have, like, originally when like I was telling people we're doing active learning or very smart versions of active learning, people were under the impression this only makes sense if I have a ton of data and I'm trying to reduce the data set to focus on something, right? Nowadays, like almost half of our users use the platform exactly in the way that you described, which is like, I have a tiny bit of data. I'm told by, my customers, by my investors, that in order to reach the performance that they hope to achieve or they want us to achieve, I'm going to need to collect data for 3 years. But that's only the case if they do it randomly, right? And so basically, like, you can use this process to say, like, as soon as like the early stages of active learning, like, is like calling for larger cars, smaller pedestrians, like specific times of day, you can measure like any type of metadata that you can possibly imagine, right? Then you can be strategic and collect just that, right? I mean, and so basically, like, we've been successful with like companies or like now I know I need to drive in the smaller streets of San Francisco after 5 p.m., right? I mean, I know that the cameras that were located in a specific location in my farm was like giving me or providing me like higher impact kind of data, right? And so now you can get the same value from your data set in just like a couple of weeks instead of like several years, right? I mean, so that's the goal, right? So now talking about synthetic data is interesting because lots of people see that as being the escape. Why? Because you don't need to annotate data. That's great, right? I mean, so we all agree that because you synthesize data to your, requirements, you can choose yourself, like, I want a car here, I want a person here, and so forth and so on, right? However, the problem you're going to face with synthetic data is, like, if you adopt a synthetic data generation process without having a strategy, then you have the mother of all big data problems, because you can potentially generate billions of records, none of them being really impactful, a lot of them being redundant, or focusing on in interesting parts of the data distribution and so forth and so on. And it's never going to help you, which is why, again, like, I believe like reducing the data as opposed to automating data labeling is really the solution, right? Because like fundamentally our problem is not just data labeling, it's like big data, right? Or like seeing big data as being necessary for for AI, generally speaking, right? And so one of the things that I always say is like, I'm all for synthetic data generation. It's becoming more mainstream, specifically for typical, like, like everyday use cases and so forth and so on. Obviously, we're not there yet for, like a very specific types of like a medical imagery or like supply chain kind of use cases and so forth and so on. We will get there, or hopefully eventually, but in every single case, while it will become easier to know how to generate data, we still don't have a solution to what to generate, right?
Yeah.
So,
Yeah.
and so it's like basically, again, like this is where you want to be like take the machine learning teaching approach or machine teaching approach as opposed to the passive machine learning approach. So I think we will all be successful with synthetic data only when synthetic data is gonna meet this sort of like a curation technology and machine teaching technologies.
No, that is so spot on. One question, Jennifer, I want to ask you is that uh, what do people have to do from a methods perspective for us to be able to interact with our trained models, where I can talk to my trained model through a natural language interface and say, hey, can you unlearn this thing that I just taught you? Can you, learn this one more? And that kind of a thing. How to, sort of communicate with a model and say, hey, I want to raise your memory, or I want you to remember this one more, or can you just go back in time? And that scenario that we ran into 3 months ago, it looks like the next few days are going to be like that. So I want you to kind of, remember more of that. So how to build some kind of communication link between these models and their human counterparts?
Yeah. No, look, so there are two questions in your question, I believe, right? I mean, there is like, how do we talk like from an engineering standpoint, right? I mean, so basically, like, obviously it's an engineering challenge because like, and that's going to be solved through like the GitLab or the GitHub of machine learning models, where like people are getting better at versioning the parameters of their models. They're still not good at documenting, right? I mean, basically what you said is like the model I was using in January was, like a better match for like the same kind of like seasonality patterns I'm seeing right now and so forth and so on. Like, I mean, we need better processes, and in the first place, it might be a human process, right? I know where somebody like from the product management team basically like documents like the strengths and weaknesses of a specific model and so forth and so on. You have an increasing like amount of like effort trying to be made in terms of like like a data drift and so forth and so on, which I think is also like an interesting and growing part of the ML ops space, right? I mean, but the engineering challenge alone is complicated, right? I mean, but like then, like it comes back to your original questions. Like basically, if you talk to a model, like are you the brain, or like you're the partner of this model, right? I mean, so indirectly, to some extent, what you're doing here is like you're machine teaching this model, right? I mean, you're basically like trying and so on. So like interacting with the model is not necessarily that hard. It's like, how do you build a feedback loop from that perspective, right? I mean, it's basically like do you want the model to like generalize, right? And so that becomes meta machine learning afterwards, right? I mean, basically to say like every third of the month, you're asking me to like, go back like 3 weeks or 3 months in time and redeploy an old model. Like, when do you want to generalize those sort of things, right? I mean, so basically like what you want to do is like maybe you teach the model and then basically you expect a meta machine learning model to control that model from afar. Maybe that's the evolution of the sort of things we're doing today, right? So it's like it's going to be an interesting area of research.
As we bring, Jennifer, our conversation to an end, would love to hear, since you have such diverse physics, math, machine learning background, what are your suggestions for people who want to learn machine learning, and maybe like you, they are coming from another discipline, whatever that discipline be, physical sciences, social sciences, or business domain? what's your advice for here in 2021 for people who want to learn it? So would love to hear. I think that'd be great. That would be a great place for us to finish our conversation today, and hopefully we'll have many more conversations down the road.
Yeah. No, look, so I mean, first and foremost, I'm gonna say so. I think people are starting to realize now that data science is very wide, right? And basically, and we completely gave up on the idea of the like magician data scientist, full stack data scientist that could do everything from top to bottom, right? And so anybody who's been in the space for long enough would tell you that to be a good data scientist, you need to be able to communicate, you need to be able to understand the purpose, why the business side of things makes sense, right? I mean, you need to be able to communicate with product managers. In fact, you should be, in many circumstances, your product managers. You should be able to prepare, analyze your data, build your models, with or without understanding the model, and so forth and so on. There are so many different facets, right? In fact, you remember, the reason why the agile kind of framework came to life, right? Scrum came to life because the agility had to come from at the same time, that you had the realization of we need agility. We also realized the same person can there is no such thing as a software engineer, right? I mean, but there are there are front-end engineers, there are back-end engineers, there are Java developers, JavaScript developers, HTML developers, and so forth and so on, right? The same thing is finally starting to happen for data, right? I mean, and so this is great because now you don't have to know everything, and it's easier to fit in the mold, right? I mean, so basically, what I say is before you read any of the advice online is basically how to become the perfect data scientist in 10 steps, or this is how I did it, right? I mean, I think the first step is basically how did you work with data? Because oftentimes people are data scientists without knowing it, right? And basically it's I've done research in the political field, but we did a lot of surveying. So basically I did a lot of data analysis. I did a lot of data collection, right? Whatever that might be, right? I mean, so basically first step is basically where does your experience stand? How did you do anything that is related to data in your space? That might be through data engineering, that might be through creating dashboards, through data collection, through designing surveys the right way, and so forth and so on, right? Once you identify this, the way you get the interest from a recruiter to enter the field is basically by emphasizing how you already did these things, right? And because one of the problems that you're gonna face is you don't have experience in this space, and oftentimes you do. You just need to recycle, and you just need to be able to market you as somebody who already did something with data in the past, right? I mean, so oftentimes it's before you jump into a Python 101, R 101, or whatever, basically try to see what type of data scientist are you? What have you done that already gives you an edge on the rest of the market? And then build on top of this, make it clear to recruiters, and then keep building on top of this as a starting point, right? I mean, it doesn't mean you cannot necessarily extrapolate or expand into other things later.
That is a wonderful advice, that the data science field, like software engineering, is maturing, and there is no such thing as a full stack data scientist. That is a misnomer. There are many different parts of the workflow, and it all depends upon where somebody can add most value and enjoy that part of learning. You earlier alluded to that ML ops, like DevOps, ML ops is maturing, has started to mature, and will continue to mature. And that ML ops maturity and this workflow-like approach, then it becomes a team sport where several colleagues with different skill sets come together to work on these types of problems. No, that's a fascinating insight, Jennifer. Thank you, Jennifer, for being so gracious with your time today. I learned a lot. I know for sure that our audience will take a lot of important lessons from that. And I look forward to our future interactions. So just wanted to appreciate you
Thank you
for
so much for having
your
me. It was a
time.
lot of fun for me as well.